Hello everyone, this is Dr. Mia again. Welcome back to ECE350. Today we're going to talk about chapter 7, lecture 17. This chapter deals with wave propagation, especially plane wave propagation. We're going to define what is plane wave is shortly. And one of the application of this is in our daily life, which is tag reader at your EasyPass, or if you go through any security, they have to read your tag. That's one of the application of plane wave propagation. Let's start here. So lecture 17, what we're gonna talk in lecture 17 is that we're gonna talk about EM waves, electromagnetic waves, which is unbounded. And also we're going to talk about time harmonic fields. One of the things is that we're going to convert our Maxwell equations from the time domain to phasor domain to apply to the wave propagation. That's the big thing for this lecture. So we're going to convert Maxwell's equation from time domain to phasor domain that you can apply them to wave propagation. So what is the bounded wave? So wave propagates through a homogeneous medium without interfering with obstacles, materials like your wave coming from your sun. So it's or your antenna radiating the wave. So those goes through the media without interfering the waves, right? That is the unbounded waves, right? And what's the plane wave? So wave normally comes out of an antenna in spherical waveform, right? Think about that. You have a antenna, your wave coming out from all direction. So it goes as a cylindrical or spherical waveform, right? But if you look the wave from far distance, you will see the fraction of it, like here. You will see a fraction of it, even though it's look like spherical waveform or cylindrical waveform, wavefront. You will see a portion of it for an observer through this aperture over here. It look like a approximately planar, right? As if it's a uniform plane wave, as if it were a uniform plane wave. What is the uniform plane wave? Uniform plane wave has the same property at every point of the plane. So, for example, if your wave going towards the z direction, right? Your wave propagates into the z direction, and you have x and y here, right? For example, x and y here. So then, if your wave, if you look at the wave from on this plane over here, x and y plane. So your wave propagating towards the z direction, going towards the direction, but your wave, if you look at on the xy plane, every slice of the xy plane, it should have the same property everywhere in the xy plane. So that's what we call planar, uniform plane wave and on xy plane. So that means on xy plane, your wave should have the same property everywhere, okay? So that's what I'm saying, identical properties at all points in the plane tangent to the wave front. So wave front is going this way. So this is the wave front going this way over here. So think about your sound wave. Sound wave goes a planar wave. Like it's pushing the air or media to go through, but every slice of the sound waveform has the same property on every point of the plane, right? That's it's called. So your wave is going as a plane. I can take one plane at a time. Yeah, this one here, another one could be over here, right? XY plane. So every plane pushing towards the z direction, but on the plane which is perpendicular to the direction of propagation, on this plane over here have the same property everywhere for the wave. That is called uniform plane wave. So guided wave, EM waves, like this wave over here, like a transmitter from your radio waves right here, is guided by the two layer. One is the ionosphere and one is the earth surface, guiding them as it goes through. It's called guided wave. And in chapter 2, we learned about that electrical wave and magnetic wave can travel together. So think about this one over here. If you have a source over here, a load over here, so your current, for example, the current going this way, for example here. So then think about that. This is positive, right? And the return path over here. So then your electrical field is going this way. This is your E, right? Positive, negative. And when current going through this direction over here, there's a magnetic field around it that is right here. So this is a magnetic field right here around it. So that's your E and H varies with VT or VT changing. So every time this VT changing, this also changing. That is the electromagnetic field traveling together through the media, and media is here is this one here is dielectric. So at this media over here, both electrical field and magnetic field, they're traveling, but they're basically perpendicular to each other, right? At every point, they're perpendicular to each other. We learned about them in chapter 2. And in chapter 6, we introduce Maxwell equation, right? So this is the time domain Maxwell equation, 4 of them. And what are they? We learn about that. E is electric field intensity. D is electric flux density. They are related by D equal to epsilon E. Epsilon is the permittivity, right? Right here. And B is the magnetic flux density, H is the magnetic field intensity. They are related by B equal to mu H, and mu is the magnetic permeability, right? And rho B is the charge density, and J is the current density. We learned about them in chapter 6. So if you see here, you can see the divergence curl. This is the divergence over here. This is the divergence over here. These two are curl, right? We have to learn about the divergence and curl in our previous classes, as well as we reviewed them in chapter 3. So how to go from time domain to phasor domain, we reviewed them in chapter 2. If you have a time domain signal over here, so go to phasor domain over here. This equivalent, right? So phasor domain, we ignore this, we just only take this, right? That's my phasor domain representation. So this is the frequency information here. We need them to go back to the time domain. So that is for E. You can also write the same equation for B, D, and H. So this is the space here for you to write the same equation for D, B, and H. All right, so now what we are doing here. So how can I go from now here time domain to phasor domain? I'm going to show you two simple things over here, how it's done, then you'll understand what's going on here. So from this is time domain, right? So if I represent them by phasor domain, and you also know that I'm going to show you this one first, right? Let's take a different color. All right, so D is epsilon E, right? If I represent both sides by phasor, to be D phasor would be what? Epsilon E phasor, right? So so D is epsilon E phasor, and rho can be also replaced by phasor domain. So that means that this equation will be here, divergence of epsilon E phasor equal to rho V phasor, right? Then you can modify that. You can take this epsilon on the other side, that will become that, right? That's what that was. That's the easy one, right? So let me show you this one here, how you get from, this is a little bit complicated, how you get from here to here, right? Let's work on that. So I'm going to use the space here, how to work on that one. I should have some space around here, but provide some space. So let's start from here. So you have curl E negative derivative dv dt, right? So now first I have to replace them using the phasor domain, right? So let's do that over here. So I replace with the phasor domain over here. On this side, negative. So for B, R E X Y Z T exponential J omega T, right? So now if I do the derivative over here, this omega t, J omega will come in the front, so negative J omega, and it would real value over here, right? So now, if you look at here, this is basically what? This is basically your this over here. You also know that b equal to let me write here, b equal to mu h, right? You know that. So if I put it here, so mu will come in front. So I can write that one as negative j omega mu, and this one became h phasor, right? So now look at that, how you got from here to here using the few step over here, right? So I use this equation over here, and I also use the phasor notation right here to do the math, right? So with that, you can do all other two to go from time domain to phasor domain. So from here to here, this is the time domain to phasor domain. This chapter we're gonna use mostly phasor domain. We're gonna also modify this one further in the next slide. I'll show you that, and so on. Okay, so that's for time domain to phasor domain. Let's go move here. So now for the last equation of Maxwell equation over here, this is the equation for the last one in the phasor domain. If I replace J with its equivalent over here, so J equal to sigma E, and take the E out, I have this part over here, right? So this part is, if I take the J omega out here, so I have epsilon minus sigma over omega. So this is called real value of the permittivity. This is the imaginary part of the permittivity. So, and it's called, completely it's called complex permittivity. So I can replace this one by epsilon c, then this equation becomes this one over here. So this equation becomes this one over here. So this is the, now with this modification, we can put that also, that is modified by that one. This one is still same, these two is still same here, right? Now how you come here from the other one, let's talk about that. So your equation over here, the what do you call it? Let's go back. Let me show you what I'm talking about here. So this one over here, let's take this one here. So that that's the equation we had. So that is right. So now, how do you get from here to here? This is in vector calculus, this is always true. If you take the divergence of a curl is equal to 0. So let's start with that. So they start from here. So divergence of a curl negative j omega mu, and divergence of, right? And this one over here is 0, right? And let me wait. Sorry. I got the wrong equation here. That should be this one here. All right. So that's right here. So divergence of a curl equal to j omega epsilon c divergence of E, right? So then this side is 0, right? 0, so that means j omega epsilon c divergence of phasor E, and this cannot be 0, that means what? Your should be 0, right? So that is right here. So this is the equation we're going to use. It's the final form of modification. This is the equation we're going to use. This is the 4 equations of Maxwell equation modified to use for our wave propagation is right here. All right. So now, again, I talked about that. The first one is the real part, second one is the imaginary part, two part of the complex permittivity. And if you have lossless media, that means what's media talking about here? Like you have seen that media could be air, could be any dielectric media. That media should be lossless. That means sigma should be 0, right? So that means second part will be gone. So that epsilon double prime is gone. That means your complex permittivity should be just your permittivity epsilon. So second point over here, I want you to think about things. What is an uniform plane wave? Think about that. We talked about it, and also what is the relation between these two here, right? time domain and phasor domain. How do you go back and forth? And what is the condition to satisfy this? We just talked about that, right? So that's all for lecture 1. We're going to stop here and we're going to get to lecture 2 in the next video.